So today I'm going to go through the NMR rules. So these are rules that are probably not going to be written down specifically in any textbooks or websites, but these are a compilation of looking through those websites and textbooks, etc. And this is a means for anybody to be able to understand how to interpret at least a 1D spectra. So these rules are just more like guidelines. They can be elaborated on further, but here I've picked out the key points. So your proton spectra is composed of protons, otherwise known as hydrogens. And what it does is your proton spectra is like a summary of all the other possible NMR experiments that could be run. For instance, like some 2D experiments, like your COSY experiment, for example. And what the proton spectra has the ability to do, that if you're able to interpret it correctly, you can actually start to divulge further into your structure and be able to understand a little bit more than maybe directly what the proton NMR is telling you. So for instance, it can tell you what environment your proton is in. Is it next to something that's electronegative, or is it next to another neighbouring proton? And if so, what does that proton look like? What's really, really cool is that NMR produces lines. It doesn't produce a picture, so it produces something that looks like this. And the chemist has to interpret these lines by following some of these basic rules, and they end up with a picture like this. Now you're looking at the two going, yeah, they don't look the same. That looks different. So what I'm going to do is I'm going to explain to you how you make this transition and that you can be able to view your picture. So moving on from there, you need to know a few things. Your spectra. What does it look like? So your spectra typically runs from left to right. You have a downfield region, which is located on the left-hand side, and you have an upfield region that's located on the right. So let's start with the downfield region. The downfield region, this is where nuclei that absorb here are found to be what is known as de-shielded. And what do I mean by de-shielded? De-shielded are nuclei that have had something taken away from them, removed. And in this case, we like to speak about electrons. So where electrons are pulled away from this nuclei, you find that the nuclei actually absorb in this region of the spectra. Whereas its opposite is where you find in upfields. These nuclei are what are known as shielded. And shielded just means that the disturbance of these electrons is not very significant, and therefore they can be found in this region here. I would like to highlight as well that I've also called regions of the spectra as outside and as well as inside of the spectra. And what I'm going to do is I'm going to discuss this in the following slides. So the things that you must remember before you start interpreting your spectra. Carbon. Carbon is totally neutral in this case. So just think of it as it doesn't have the desire to steal anything from anybody. And in doing so, it doesn't influence where your peak starts to fall in relation to your spectra located at the bottom. Atoms, however, like the electronegatives, nitrogen, oxygen, and even some halogens, they like to steal electron density from their neighbouring protons. So like we discussed in the previous slide, if you are stealing something or you are de-shielding it, you are moving in this direction of the spectra. You are moving to more of the downfield region. The same is opposite, that if you are not stealing anything, for instance like this carbon species, you are therefore staying within the upfield region of the spectra. So there are two things. I have written here outside and I have also written here inside. What do I mean by this? So outside, I want you to imagine that you were somebody wearing an awful lot of clothing and you were standing outside. If I am, for instance, bigger and stronger than you, I want to take some of your clothing. And in doing so, if I take some of your clothing, I'm stealing your electron density, as it were. You get cold and you start to move inside of your spectra, or inside a house or inside a building, etc. The more layers of clothing I steal from you, the further and further inside the spectra I come. And this seems to be quite a weird technique to explain, but over the years of teaching this, I found this is actually to be quite effective for teaching people who are not chemistry related, to get them to think about this inside and outside of your spectra. So, rule number one, let's start with the rules. It's all about the rules. So, your regions of your NMR, these are some things to pay attention to. So we're going to start off quite large, and then we're going to break it all down into do the finer bits of detail. So this is a starting quite large. Your spectra in a proton runs typically from 0 to 12, where 12 you can find is the most de-shielded, which means you're in the downfield region, and 0 is where you can find the upfield region. Now this spectra is measured in ppm, otherwise known as parts per million. You have your regions, so I blocked them off in threes. So you've got 0, 3, 6, 8, and 12. And as you can see here, by looking at the structures that I have written in these different areas, you can see you're becoming more and more electronegative as you start moving along the spectra, with the most electronegative being your acid and your aldehyde. What do these two groups have in common? Well, they have this in common. They have the carbonyl species. If you are familiar with your chemistry, the carbonyl species, the oxygen steals electrons from the carbon, and in doing so, it creates a pull on the bond. In doing so, you get what is known as a partial negative charge and a partial positive charge. Ignore my really horrible attempt to draw on this. So you get a partial positive and a partial negative charge. This is signifying the carbon has lost something and the oxygen has gained something. You have your aliphatics, which are typically your CH3s, your methyls. It can be long chains, for instance, like heptane, hexane, for instance. You then move in your region of 3 to 6, and you find that you start to incorporate some of this electronegativity through double bonds, for instance. However, what's not written on this diagram is actually the heteroatoms. Well, where do the heteroatoms fall? Heteroatoms tend to fall between the regions of 3 to 6. However, it depends on what that heteroatom is attached onto. They can be found closer to 3 or they can be found closer to 6. And how do we determine if something starts to move within its region? Well, we will discuss that later on. So for now, just remembering the regions of the NMR, we start off with how to start interpreting our spectra. Moving on to the next important rule, rule number 2, peak splitting. So I said to you that the NMR can tell you how many neighbours does another proton atom contain. Is it something that doesn't contain any neighbours, or is it something that does? And if so, what sort of environment are they in? So right now what we're going to do is we're going to actually start to discuss this, what is known as peak splitting. We want to find out how many neighbours, and there's a general rule of thumb, the N+1 rule. N stands for the number of neighbouring protons, and then we add on the addition through +1. I want to actually tell you just now that is beyond the scope of this tutorial to explain the shapes of these peaks. For now, we are just discussing how peak splitting occurs. So let's take our first peak, for instance. Here we have 2. So after writing out the formula of N+1, and we say that it equals 2, again, look at this shocking. Yeah, that's my best I can do on this one, okay? We find out that N is actually equal to 1. So if this peak splits into 2, we know that the number of neighbouring protons that this proton can see is 1. And is this true? Yes, when we do look at it, it contains 1. By looking at the next, we see that it splits into 4. So using the rule of N+1 is therefore equal to 4, we know that this species has 3 neighbouring protons. And the same could be said for the last peak where it splits into 3, that its N number is actually 2, so contains 2 neighbouring protons. So let's now start to divulge into, well, where do they start to fall in the spectra? So we've looked at regions, and we've also now looked at how they split. So we start to talk about the electronegative atoms. And what this is, depending on the shielding and deshielding effects, depends on where they fall within the spectra. So the more electronegative, which means it is taking electrons from the bond or stealing or has a greater pool of these electrons, you will find that this becomes more deshielding. And I said to you, deshielding falls more inside your spectra, so over in this region here, or downfield, otherwise known as. So let's take our first species to look at. Here we have ourselves a CH3. So the CH3 is attached onto an aliphatic chain. So automatically we should be thinking in this aliphatic chain, it should fall within the aliphatic region of 0 to 3. We therefore then start to say, okay, well, what are its neighbours? So let's look at its neighbours. We have here a carbon species. This carbon species contains 2 hydrogen atoms on it. So we're drawing here. Now we use the rule of N+1. So we know the number of N this time for these blue CH3s. We know that its number of neighbours is 2. So 2 plus 1, therefore this peak should appear as 3. Where should it fall? Well, it should fall within the region of 0 to 3. How close it is to 0 to 3 is determined by what it's also attached onto. Carbon, as we said before, has no desire to steal anything. So therefore, if there's no pulling power on this bond here, therefore this peak should fall closer to 0 than it should do to 3. But let's take another example. Let's start to look at these electronegative atoms. So here we have ourselves this methyl group, which now is attached onto the oxygen species. Let's do what we did before. This methyl group is still an aliphatic, so it should still fall within this region of the spectra. However, this time, let's now look at our next rule, which was peak splitting. How many neighbouring protons does this group see? And here, it's now the carbon is being replaced by an oxygen. Therefore, it doesn't see any. So using the rule of n+1, we should therefore see one single peak within this region of 0 to 3. However, now the NMR can tell the difference between that this one was connected to CH2 and this one's now connected to an oxygen. So an oxygen is electronegative. It is pulling on the electrons from this bond. It's stealing what doesn't belong to it. And in doing so, it's starting to de-shield these hydrogen atoms here. In doing so, would it be closer to 0 or would it be closer to 3? Now, using our knowledge from previous, we know that it should start to move further up the spectra, as in towards the downfield or inside region. And in doing so, we expect that this group should start to fall closer to 3. So taking a look at it in the next slide, we see that we do have a single peak, as we discussed earlier, and this single peak is indeed actually found closer to 3. But this doesn't stop here. So let's take a look more into these electronegative atoms. You've got OHs, you've got NHs, you've got SH. And these are what are known as exchangeable protons. Because the exchange is very rapid, we don't see these nice peaks, clean peaks that we see here. What we see is we see what is known as line broadening, where we see these fat and lazy peaks, as if it were. And what this happens is this is identifying that you have an exchangeable proton in your spectra. So anytime you see something like this in your spectra, you should be flagging up by saying, hold on, actually, I could have one of these elements present in here. And if so, which one is it? So taking here, we have the example benzoic acid. And now what we're doing is we're focusing more on this OH. Now this OH is attached onto the carbonyl species. And we said before, so let's start using our rules. Rule number 1, where in the spectra would this fall? We knew that acids fall between 8 to 12. So we're talking about this region here. That's fine. We then said, okay, peak splitting, how many neighbours does it have? And we look here to say, actually, it doesn't contain any neighbours. It's got a carbon, which is attached onto the oxygen species. So therefore, should only appear as a single peak. But because now we know that OHs are exchangeable protons, we may see a single peak, but we may also see this line broadening because the exchange of these protons are very, very rapid with the sample. And in doing so, any water, so this is also another rule as well, any water that's present in the sample can also cause this exchange. So what happens is that this proton becomes exchanged with the water species in the sample, and in doing so, the NMR is detecting this exchange. If the exchange is rapid, you are not going to see much of a peak, as in a nice sharp peak. You're going to see one of these broad peaks here. So this also takes us on to our next rule. Our next rule is solvents. Now, you don't want a lot of water in your sample. You might see a lot of this exchange occurring. You might never see what it is that you're truly wanting to see in your molecule. Does it have an OH? Does it have an NH? You might not be able to see this because sometimes that line broadening can be so broad that your peak actually merges with the baseline and it's not possible to see it. I love as well how I'm also doing hand gestures and you can't see anything of my hands. So, moving on from here, solvents. If you take 1 milligram of sample and you dissolve it in 500 microliters of a given solvent, so let's for instance think about methanol, ethanol, chloroform, dichloromethane, DMSO, they all contain protons on it. Which one do you think the NMR is going to be able to see? Your compound or the solvent? And the answer should be flagging to you straight away. It's definitely solvent. I mean, there's so much of it there. And you'd be correct. The NMR would become completely saturated by this solvent. Now, that's not really good for us because we want to be able to see our compound. So, what do? Well, what we do in NMR is we exchange out all of these hydrogens and we exchange it for the element deuterium. Now, what is deuterium? Deuterium is heavy hydrogen. So another little rule for you to remember is that proton NMR can measure spin states of a half, 3/2, etc. And what do I mean by this? So with deuterium, deuterium contains a proton, but it also now contains a neutron. And in doing so, it now has a spin state of 1. Because my spin state is not half or 3/2, which is like can be seen for a proton, what happens is here is that it now becomes NMR silent. So anything now that contains a deuterium, the NMR cannot read it. So this is how we managed to eliminate the presence of solvents in our sample so that we can read purely just our compound of interest. More detail into where you can find about spin states and what the NMR can actually read can be found in later on tutorials, but it's beyond the scope just now to go through this. So the next rule, another major and most important one, is equivalent protons. So far we've gone through our spectra, we've looked at all the different regions in the spectra, we've then said about how do our peaks look to us, how do they split, 2, 3, 4 peaks for instance. We've then taken a look to say about exchangeable protons, so these are things that polar atoms that we see in quite an awful lot of drug molecules. And then we then started to talk about solvents where we say, well, how do we actually read from the spectra? And now what we start to look at is the equivalent protons, because there are some compounds out there that have areas in it that are symmetrical. They have identical regions on it, and the NMR can actually detect these identical regions. It might not be able to distinguish the differences between both of them, but it can tell you that it's present in the sample. So let's look again at benzoic acid. Benzoic acid, if I was to draw a line of symmetry through the middle, I could see that the hydrogens that are located in blue, or identified in blue, are identical. I cannot tell the difference between this one, or I cannot tell the difference between this one. So the NMR detects this, and the NMR says, well, actually, I know that both of these are within the same distance to this carboxylic acid group, and therefore I'm going to put them together. So, for instance, if I'm going to draw on extra hydrogens, so let's just draw on the rest of these hydrogens onto this aromatic ring, again with my beautiful, beautiful drawing, no laughing. So here, each one of these hydrogens, let's use the n+1 rule. How many neighbours do each of these have? So we look and we say, this hydrogen species contains one neighbouring hydrogen species. So using the rule of n+1, he should appear as 2 peaks. Let's look at this here. The number of neighbouring groups is 1. Using the rule of n+2, this should appear as 2. However, because they are both identical, the NMR merges these two together. And in doing so, it forms a peak that looks like this. This here is signifying that you have 2 peaks. So let's read off just the highest peaks for now. We will not speak about just now the smaller peaks, again beyond the scope of this NMR rules, but will be mentioned in later on tutorials. Here we can see the 2 major peaks. There are 2 peaks here. And in doing so, this is what we hypothesized. However, the NMR is able to read the 2 identical protons, and in doing so, it creates this, what is known as an integration number underneath. And what it's doing is it's measured the area of the peak, and it said to you the number of protons equating to this sample is 2. So it's telling you that not only is there, each one of these has one neighbour, because the n+1, but also it's 2 protons that are counting for it. And because they have managed to merge together, they must be identical. This might look a little bit weird by looking at it from this sort of perspective, so let's take it back a notch. Let's look here. Here we have the starting molecule that we saw on the very first slide. We have an OH and we have an NH2, and they are located para-substituted, which means 1 and 4 position of the ring. Like we did previous, if I draw a line of symmetry down, so we can see that there are identical protons, and here the red protons are within the same distance to the OH, and the blue protons are within the same distance to the NH2. And you can agree by looking at it, the blue and red ones are not identical. They are in different environments based upon these groups that are attached onto either side. The NMR can read this, and the NMR then says, okay, the red ones have one neighbour, the blue ones have one neighbour. Using the n+1 rule, they appear as 2, And here, the integration value, like we spoke about just in the previous slide, it's saying to you there are 2 protons making up the sample, but the protons have only one neighbour between them. Again, let's divulge and let's look at some more examples. So here we have ourselves the aromatic signals. So here the NMR has the ability to identify substitution patterns or an aromatic ring. So aromatics, like we said before, we look between the regions of 6 to 8 on the spectra. How far they fall within this region depends on what they're connected to. So here we have our aromatic benzene ring, and now we're going to start to look at substitution patterns on each one of these rings. The first, let's look at it here. So the first thing to do is when you get a structure, start to identify all the protons on that spectra, and what to do is categorize them, which ones are the same and which ones are not the same. So here we have a methoxy group attached onto our aromatic ring. The red protons are closest to the methoxy group, so appear as one group. The blue protons, you cannot identify the difference between either in the same environment, so this is group number 2, and the green ones are group number 3. The green one is on its own. Now using the n+1 rule, the protons in blue have one neighbour, the blue, and therefore appear as 2. The blue protons have 2 neighbours, the red and the green, and would therefore appear as 3. And the green protons have 2 neighbours, although they are identical, but it still has 2 neighbours, would therefore appear as 3. So that's fine. However, something about the order at which they fell. Why did the blue ones come first? Why was it followed by the green? And why was it followed by the red? So what we can do is we can actually take a look at another example here to help us. So here what we've got is we've got ourselves our acid again, but this time that we have now made it an ester for the sake of. So we know how to start to categorise these. So they're categorised into groups and the details of which won't be given because we've just discussed them here. So the splitting is identical. Look at the splitting. The red contains 2, the green contains 3, and the blue contains 3. The same as can be found in this example here. However, look at the order. Why has the order changed? And this is where we start to look at electronics. What is the substituted group doing to that ring? The oxygen contains a lone pair, and in doing so, this lone pair feeds into the ring. When it feeds into the ring, it creates a partial positive and a partial negative charge. The partial positive can be found on the oxygen, as the oxygen will now resemble 2 bonds to your ring. We do like so. That's the best I can do for the ring on this one. And in doing so, because the arrows have moved on to the next neighbouring position, we have ourselves a slightly negative charge. In doing so, what we can say is that there are more electrons present in this position than there are that's now attached onto the oxygen. Through the resonance structure, if we start to keep drawing this, we will find that the negative charge can then move again and therefore that now be found on the 4 position on the ring. So what happens is that when you have this electron donating species, as you see here, the positions that are affected are position ortho and position para. And in doing so, if you are giving electrons, so you're giving clothing to that species, they should fall more within the upfield region of their spectra, 6, than they would do to 8, because they have been given electron density. The meta position, which is located by the blue protons, are not affected by this group being added, and in doing so, it remains higher up in the spectra, or more downfield in the spectra, than the other 2 peaks. So let's take a look at its opposite. A carbonyl species, we said, likes to pool electrons, and in doing so, if there is a pool of electrons, we again get this partial positive and partial negative charge. The oxygen now in this case gains the negative charge, and the carbon species gains the partial positive charge. And in doing so, it's saying here now that the ortho position has lost electron density and the oxygen has gained. If we keep moving these electrons, known as resonance, around the ring, we can therefore see that it's the ortho and para positions that become most affected by this group. However, the electron density is poor at these regions in comparison to its electron donating species where they were rich. The sites therefore that are most affected are the ortho and are the para. Because the ortho is in closer proximity to the carbonyl group, it appears higher up. Whereas you would find actually the blue and the green protons, these groups would actually be quite close together, and here I've just drawn them blue followed by green, but they could be highly close together or even maybe merge or overlap with one another. So let's take a look at some more. Here we have started to add on some groups. So here we have a methoxy that we learned before was electron donating, so it feeds electrons into the ring. A methyl group, a carbon, is virtually neutral, so it doesn't take, but it has the option to give, but just a little bit give. And we found out if stuff wants to give electrons into the ring, we found out the positions that are most affected are ortho, signified by O, and para. And therefore what we see here is the site that is most affected, because the oxygen is more electronegative than the CH3, that the position that would be the most affected are the protons signified in red. Are they signified in a good way or a bad way? Well, if they've been given electrons, it's a good way. So here we've shown that they fall lower down in comparison to its blue counterparts. Let's take another example. So here we have electron donating, feeding electrons into the ring, and we have an electron withdrawing, taking away from the ring. We said that the ortho and para positions were the most affected by this. And which one is the most affected? Well, we see here that the blue protons have electron density sucked away from it, so would appear more towards 8. And the ortho, or the red protons, are being given electrons, so would fall more towards the 6. And you can actually see this by the spectra here, that the gap between these two have become quite large, signifying to the reader, the viewer of this, is looking at going, okay, there are two different environments, two very different environments. One is pulling electrons severely and the other not so. We will then take a look at our last example here. So these all so far we've been talking about para position. That's great, but not everything falls in para position, not everything falls in meta, not everything falls in ortho. So now we just want to look at another example. Here we have these two same groups, so remember donating, and we have withdrawing. And now we want to see, well, what rings are the most affected, well, which protons are the most affected? Again, always draw in your hydrogens first, so we've drawn them in. We identify the different ones and similar ones, and here I've colour-coded, red, purple, pinky sort of colour, blue and green. We then look and say, okay, which ones are affected? So, by donating, we have a negative charge in this position and a negative charge in this position. Because this group is para, we also have a negative in this position. The position that remains unaffected by this methoxy group is the blue protons. We then take a look at the electron withdrawing species, so in this case our ester, and we say the one that is most affected is ortho, so this site also now gets a positive. This site here also now gets a positive charge, and this site here also gets a positive charge. So what can clearly be seen here is that the blue protons are the ones that are least affected. Because they are least affected, we know that they should be more upfield or closer to 6 than the others. Here we have which one comes first in the spectra. So we have the option here of the purple, pink, or the green. Which one was to come first? This site here, the green protons, are furthest away from the methoxy group, and therefore having a least influence compared to its ortho counterparts. In doing so then, the green protons has the most affected by this electron withdrawing species, and therefore would appear higher up in the spectra, or more downfield. The same therefore is true for when we start speaking about these two protons. The red proton is least influenced by this withdrawing group because it is furthest away, yet still the charge is carried. And the same therefore can be said by this species here, by the purple one. The methoxy and the ester group are both ortho to this group here, so you have donation and pulling away of these protons. So therefore, the group therefore, now that it becomes the more affected, looks to be like the red, because it is furthest away. Is it a good or a bad thing? Well, actually, in this example, it's actually quite hard to tell. Again, you would probably get merging of these two peaks together, but here I've said that the red would fall first, followed then by the pink-purple colour. In reality, these could be merged together because they both contain these two charges. Both of them are within ortho to this methoxy group. However, this one is also ortho to its electron withdrawing group. So it depends on the strength at which electrons are being pushed in, to which the strength of the electrons being pulled back out. So here, they can be found, so they are written red and purple or pink, but they can be found in either way. So I hope so far this is just a guideline to the basic of NMR interpretation, and it follows these set of rules. And like I said to you before, these rules, they are not referenced because they are taken from many books and many years of studying, but the information out there on the World Wide Web is vast, so do take a look at some of these. But like I said to you, these sets of rules are to help people, even of the non-chemistry nature, be able to start to understand how does the NMR start to interpret your spectra. Now, it depends on your background. You may not be a chemist, but at some point you might actually have to look at some of these spectra and be able to have a rough idea, either to help your chemist or you might actually be the only one on your project. So I think that these are very worthwhile rules to be able to understand your proton NMR spectra. For any additional topics that were mentioned here but were not gone into detail can be found further in some of our tutorials section.